Hello, my name is Dr. Abrahamian, and in this channel I go over problem-solving strategies mainly as it relates to math competitions. So here is a problem from the International Math Olympiad in 2024. This is shortlisted problem N2. Determine all finite non-empty sets S of positive integers such that for every A and B in S, there exists a C with A dividing B plus 2C. So I'm going to walk you through the process of obtaining the solution. The first thing is, let's say S has only one element. Well, clearly this condition is satisfied because there's only one pair. It's just A, and A divides A plus 2A. So every subset of size 1 satisfies this property. Now, let's say you have two elements, A and B. So what do we need? We need A to divide B plus something. So it would be either B plus 2A or A divides B plus 2B. So these are the only two possibilities. Now, this guy tells you that A must divide B. So depending on whether A is smaller or A is larger, this would be possible or impossible. So let's assume that A is less than B and see what we get. So this one tells us that A divides 3B. Now the other condition is B must divide A plus 2A or B divides A plus 2B. So this one is impossible because this is the same as B dividing A, and B is larger than A, so that's not possible. So that means B has to divide 3A. Okay, so what are the properties that we have? We have that A must divide B and B must divide 3A. So this is what we get. Now, what does this mean? It means B is equal to K times A, and then we know that 1 divides K divides 3. So there's basically two possibilities. Either K is equal to 1 or 3. So in fact, there's really just one possibility for a set of size 2, which is A and 3A, but of course A could be anything. So now I'm going to look at the case when S has 3 elements and see what I get. So I have A, B, and C, and let's say A is less than B less than C. So what are the conditions? We need A to divide B plus 2 times something. It could be B plus 2A, or it could be B plus 2B, or it could be B plus 2C. And we have something similar for B, and we have something similar for C. So if I write down the one for C, that's a little bit stronger. So I get A plus 2A or C divides A plus 2B. These are really the only two possibilities, because the last one, which is C divides A plus 2C, is really not possible. Okay, so now what does this tell us? So the first one tells us that C divides 3A, and the second one tells us that C divides A plus 2B. One thing that I notice is that if A, B, and C have something in common, I can divide off by whatever common element that they have. So in other words, if I look at S that satisfies this property and D is the GCD of A, B, C, then I can just replace S by this new set A over D, B over D, and C over D. This is the new set. In other words, I can assume that GCD of A, B, C is equal to 1. And I'm going to look at the set A, B, C. And whatever answer that I get here, then I'm going to multiply by A. So let's see what I get. So I get C divides 3A, but I know that A and C are relatively prime. So that means C must be 3, because C must divide 3. So that's C equals 3, but A is less than B less than C, which means the numbers would have to be 1, 2, and 3. So this is really the only possibility. Now let's look at this and see if there are any possibilities for this, if this fact in this satisfies the conditions of the problem. So we want 2 to divide 1 plus 2 times 3. That's not possible because this one is odd and this one is even. So right there we get two conditions that is pretty obvious. The first one is we may assume that GCD of elements of S is 1. The second one is if A and B are in S, A is even and B is odd, then what I'm going to get is A divides B plus 2C is impossible because this one is odd and this one is even. So in other words, I can deduce that all the elements of S must be even or all elements of S must be odd. But because their GCD is 1, all of the elements are odd. Okay, so we assume that S equals A1, A2, all the way to AN, and AJ is odd, and GCD of A1 through AN is 1. And let's assume that A1 is less than A2, less than AN. Now let's write down the condition that was the most helpful for us. So we know that AN must divide AJ plus 2AK. Now this guy is too small to be divisible by AN, because if I look at AJ plus 2AK, that would have to be less than 3AN. But it's a multiple of AN. So that means the only possibility, because this is odd and this is of course also odd, the only possibility is if AJ plus 2AK is equal to AN. So what does this tell us? Because of course J isn't equal to N. And this is true for every J. Now I can write this down for other J's also. So for example, A1 plus 2AK is equal to AN, but so is A2 plus 2 some AL. That's also AN. So if I look at this one and I subtract these two, I would get that A1 minus A2 plus twice AK minus AL is equal to 0. But this is even. So what does this mean? It means A1 is congruent to A2 mod 4. So A1 is congruent to A2 mod 4 because AK minus AL is even. So I can do the exact same thing for every two numbers in this set. So this tells us that A1, A2, all the way to AN minus 1 are congruent to each other mod 4. And I'm assuming that N is at more than 2. I'm going to start from N equals 3 and above. So let's see what this gives us. Now, if I write down the exact same thing, I have A1 plus 2AK is equal to AN, and I also have that A2 plus 2AL is equal to AN. Subtract these, and you get A1 minus A2 plus twice AK minus AL is 0. So this is congruent to 0 mod 4. Therefore, A1 must be congruent to A2 mod 8 this time. And repeating the exact same argument, we know that A1, A2, all the way to AN minus 1 are congruent to each other mod 8. So of course, this is a contradiction if you repeat this process. So repeating, we get that A1 all the way to AN minus 1 are congruent to each other mod 2 to the K for every K. And what does this mean? That means A1 through AN minus 1 must be the same. So therefore, in fact, N must be 2. So either 1 or 2. So the answer to the problem is either S must be a singleton or S must be A3A. And that brings me to the end of this video. I will see you in the next video.